Good afternoon, everyone. Welcome to IME 765. Today is April the 15th. We're going to continue our topics on regression. First, again, let me stop my video and share the screen. Screen share. Okay. And let me take my annotate here so that you can see. By the way, if during my class, if you have any questions, please feel free to ask me. Before, first unmute yourself. Otherwise, I cannot hear you. Okay, so in the last class, we mentioned, if you don't mind, let me directly use this Text Studio, because in case I have any, mistakes, something, I can directly, fix it here. So in the last class, we mentioned what? We have finished this part, right? The statistical part of the y and the beta itself. And I think I already proved this one, right? The RSS over sigma square follows the chi-square distribution with the degrees of freedom of n minus p minus 1. I proved it already, right? Last time, right? Hello? Okay.
Yes.
Can you hear me? Okay, okay. And of course, because if this one's correct, then you just, do something very simple, move the sigma here, and then because the chi-square distribution equals the expectation of chi-square distribution equals to the degrees of freedom, so you immediately have this one, you just move it, then you get an unbiased estimator of sigma squared. Okay, so that's the reason why when we're doing the linear regression for p features, actually p plus 1, because the 1 is actually the beta 0. We usually use this one to do the sigma square instead of the traditional method, which is n minus 1. Remember? Okay. So this is thing number 1. Thing number 2 is the hypothesis. Yes.
About the equation number 20. Is
Yes.
it true only for linear regression, or can I use for nonlinear regression by using the degree of freedom instead of p plus 1?
First of all, this is a very good question, Arab. Think about this, Arab. When you're doing the nonlinear regression, right? How would you understand the nonlinear regression? How do you define the nonlinear regression? Let's say this. Suppose you say, okay, I just use the least square method. Let's say suppose that's a polynomial, right?
Okay.
Be careful that a polynomial can still consider it as linear regression. You know why? Because again, use the coding method. Remember what we showed here in the very beginning of the page. You can consider, for example, x1 equal to x1, x2 equal to x2 squared, for example. X3 equals to x1 times x2. You know what I mean? So in this case, you're absolutely correct. Yes, you can use this, no problem. But be careful. If it cannot be equivalent to return something like a polynomial. Say it's some hyperequations. Now, hyperequation cannot do the regression. Let's say it is some exponential. Let's say exponential equations, right? Then you need to be very careful, because exponential regressions, for regression of this kind of exponential numbers. For example, consider let's say the logistic regression. I have exp and to the power of something. And again, I suppose I cannot easily linearize it or something. For example, you cannot, for example, get the log of y and then linearize the right-hand side. For example, suppose you have something very weird. For example, a sine, let's say beta 1 x1 plus, let's say exponential of something, blah, 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 right? So in this case, no, this is wrong. You cannot claim in this way. However, there's another interpretation. Even if for this case, I can still do something else. That I make one function to be x1, the other function to be x2. You know what I mean? And then for each of the x, I will use each of the function, I can linearize it and make it in this way, and then construct as the summations of the functions.
Okay.
You know what I mean? Then it's gonna be a combination of many things. That's another story. But in most cases, we like this kind of polynomials, right? And the answer is yes. For polynomial, you can still do this way, but you have to smartly apply it, kind of like coding it. Okay. So this is, by the way, this is just a unbiased estimator. You can never claim that unbiased estimator is always the best one. No, you cannot claim it. You know what I mean? Why people like unbiased estimator? One very important reason is because of its name. It's unbiased. So why unbiased is good? Because simply because people feel that it is fair, but you cannot guarantee that it is always the best. So in many cases, to be honest, people directly use n-1 instead of n minus p minus 1. You know what I mean? I'm not telling you that this must be the best, because you have to define what does best mean. I'm telling you that this is an unbiased estimator of sigma square. However, actually, if you have this book, right, the ELS, right, you go there, you're gonna see. Let me see which chapter. Let's see. There's the chapter 3.2.2, 3.2.2. By this Gauss-Markov theorem, it actually tells you that the least square estimator is has the smallest variance. So this tells you that the LS solution is actually a very good solution, which gives you the smallest variance among all unbiased estimates. Okay, what I mean is this. I'm not talking about this. I'm talking about this. So from here, where it is, from here, we know that this beta hat, which is the OLS estimator, is unbiased, right? Because the expectation is beta. And the Gauss-Markov theorem tells you that this is the best one with the minimum variance. So in terms of small variance, yes, it tells you that OLS is the best one. However, in general, we cannot guarantee that we always define this is the best. You know what I mean? So, so I don't know whether this answers your question.
Yeah. So I have another question.
Yes.
Can I ask another question?
Of course.
So can we say that OLS estimation is always unbiased?
Sorry, which is always unbiased?
OLS estimation.
Of course, of course. Why? It's already proved here. See, it's proved. Here's the proof.
Okay.
So of course, I assume you are talking about the linear regressions, and the OLS is defined in this way. Okay, then yes,
yep.
Here's the proof. And also, this sigma hat using this way is always unbiased. Why? Proof. This proof is super simple. Everybody can do it. But to be honest, this one is not that easy. Usually you need this step. This is really not easy. I mean, I tell you the answer, it's easy to verify. But to think of this, you know, so many great mathematicians thought how many years, how many decades they got this. Okay. So any other questions? No? Okay, today let's continue. I remember I finished this part as well, right? The hypothesis testing for a single beta j, right? This tells you a single coefficient j, whether it's significant or not. So if you fail to reject the null hypothesis, which is, let me see, where did I? Okay, let me underline it. Here's a null hypothesis versus beta j is not equal to 0, of course. If you fail to reject it, that means what? That means beta j is not that significant. Kick it out. So that in your next trial, you don't have to include this beta j, okay? And this is nothing but actually the t-test, or if you want, you know, a lot of n, I remember Said last time you mentioned like greater than 40 or 30, you can use the z-test, it doesn't matter. I assume you have already learned this, okay, in whatever statistical courses. This is a very, very simple, just very standard, you know, methods for, let me draw it, for you know, this kind of, no matter t or z, whatever, the same, you know what I mean? Something like that. And this part, oops, so ugly, whatever. Okay, so that if it's outside, then rejection, inside the fail to reject, that is that, and the confidence interval is from here to here. Okay, so that's the case. Okay, let me clear. And now today, let's introduce something about what if we want to simultaneously consider a sequence of the coefficients rather than one coefficient. So what is the point of that? The point is that, for example, suppose we have some categorical this kind of coefficients. In other words, for example, consider multinomial distribution. Multinomial distribution or multi-nullity distribution. For that kind of cases, what we usually do to have several to have several vectors, right? For example, suppose I have, let's say this, suppose I want to see whether, let's say, some number, some response is related with gender. So I'm going to consider male or female, but I don't have to just use 0 or 1. What I can do is that I can create two vectors, for example, the beta 1 and the beta 2. So it's going to be either 0, 1 or 1, 0. 0, 1 means, for example, it's male. 1, 0 means, for example, it's a female. So if we want to really determine whether the effect of gender is significant or not, we have to consider beta 1 and beta 0, beta 2 simultaneously. It's meaningless just to delete beta 1. Oh, you delete all beta 1, then what does it mean? That means everybody is male. Or you delete beta 2, that means everybody is a female. You know, it doesn't make any sense. So you should either keep beta 1, beta 2 together or remove them together. That's the point why we need to consider like this way. So mathematically, what we do is this. Suppose the big model is, let me make it a bit bigger because, okay. Suppose the big model as beta J1 to beta J P0. And the smaller, the nested smaller means I choose something from here. The smaller model is beta Ji1 to beta P1. So P0 means the original one, which is bigger with J. And and the P1 is something smaller, okay? And of course, we have J1 is, we have I1 to IP1 is a subset of J1 to JP0. For example, suppose your J1 to JP0 is beta 1 to 10, for example, 0 to 10. Let's make the life easier. And for example, this part, your beta J, a small group is, for example, beta 0, 0, beta 0, beta 1, beta 2, for example. Okay, now, first of all, we must have RSS0 is less than or equal to RSS1, where RSS0 is the residual sum of square of this part, the original model, and RSS1 is that of the new model, the smaller model. Why? Simply because the optimal solution of this part is still a feasible solution to this part, okay? Which is a special case that, for example, here we mentioned is your beta I1 to IP1 are still the same, but all other betas not in this part. In other words, what I mean is that it is in, let's say, J1 minus this part, all others equal to 0. It's a feasible solution in solving this. That's the reason why this must be less than or equal to RSS1. This is the first. Second thing is, okay, now let's consider a parameter beta j is not in, a beta j is in the big model, but not in the small model. And I want to ask whether they're significant or not. So your new null hypothesis becomes this. I want to test beta j equal to 0 for all j that is in the big model, but not in the small model. I want to see whether it's significant or not. These beta j's together significant or not. If it's not significant, I'm going to kick all of them. That means I'm going to accept the small model. If it is significant, then I'm going to, consider all of them. In other words, I'm going to reject the small model. Okay, let's see. So first of all, by this RSS, okay, I will have this as, chi-square distribution with degrees of freedom of m minus p minus 1. And then I'm going to use this one minus that one. Then divide by sigma square again. So this should follow a distribution of chi-square, still chi-square distribution. Why? Because chi-square distribution is what? The summation of normal distribution, square normal distributions, right? You use one part minus the other part, and the other part is a subset of this. That means what? You already minus all this part out. In other words, the one left here gonna be what? Gonna be independent. And this gonna again follow the chi-square distribution, but the degrees of freedom here equal to the first degrees of freedom minus the second degrees of freedom, and finally here it equals to P0 minus P1. Again, P0 is the bigger model, P1 is the smaller model, so of course P0 must be greater than P1. Okay, and now we have this one. What we can do is to take advantage of the F distribution. Still remember F distribution? It is here. This is the theorem. So F, can you see it clearly? Let me make it a bit bigger. So if I have one as degrees of freedom, this one, y2 degrees of freedom of this one, they're independent, then y1 over d1 divided by the y2 over d2 must be F distribution of d1 and d2. Okay. So so where it is? So it is here. So here we take the advantage of this, and I divided by sigma together, so the sigmas cancel. So I have this form, and by that theorem, we know that this part must follow the degrees of freedom of p minus 1, degrees of freedom of F distribution with the first df as p0 minus p1 and the second df as n minus p0 minus p1. Again, I assume n is bigger than p, much bigger than p, so it doesn't matter p1, p0. Okay, so you may ask why they're independent. Because of this, in the denominator, in the numerator, I use RSS1 minus R0, RS0. In the denominator, I use RSS0. You see, here in the numerator, RSS0 is eliminated already. That's why they're independent, okay? And clearly for the RSS0, the df as n minus p minus 1. And for the numerator, the df as p0 minus p1. And that's the reason why this must follow an F distribution. Clear? So now it's clear. I'm gonna test this this is called F test. I think you have learned, right? F test. So the F test should look like this way. Look somewhat like, so ugly. Let me redraw it. It should be something like, sorry, I don't have the talent. Enjoy. So this is gonna be the alpha part. Okay, anyway, let me find a Google. Anyway, I really don't have any talent in drawing. Let me find a Google thing. Let me see it here. Okay, so I have the F test, and let's see. I should have something. Oh, okay, here. You see, not too bad. Okay, except for this part should be a bit bigger. Something like this way. See it? Okay. So this is the F test. Okay. So here we go. So if your test F is greater than or equal to the critical region, then the null hypothesis is rejected. Rejected means what? Means these beta j's are important. You cannot reject this. Okay, you have to take the bigger model. If it's not rejected, then yes, all these groups of the beta j can be removed. So for example, as I just mentioned, you don't have to consider gender. So both beta 1 and the beta 2 will be removed. Okay, so in this case, these are the most important things now hypothesis testing and the confidence interval part and they are super applied. Why? Because when you're doing the linear regression model, you're gonna do it. You know what I mean? Because simply you don't know which one should you consider, which one you should not consider. In some cases, remember the what is the example in the logistical regression? Let me open it. Logistical regression, which is chapter 6. Let me see where it is. It's here. Okay, so here we do have an example here. Remember it, the South African heart disease. For example, in the very beginning, you have so many, right? And from the part of interpretation, it doesn't make sense. For example, we mentioned that the obesity, it is negative. How come? Usually, if a person is very fat, overweighted, then he or she would have a very, very high chance, right? One reason, because there are some cross factors that these ones already included. That's the reason why you're gonna see it's kind of like negative. And to this end, we do the z-score test and we remove one by one. Remember it? And until we cannot remove that, all of them are significant. For example, you can consider alpha equal to 0.5%, I mean, then 0.975, which means 97.5% of the normal distribution point is where? 1.96, right? Okay, so in this case, let's say 2, it doesn't matter. As long as everything is greater than 2, then accept. So this is actually an application of what? An application of this, that we consider elements one by one. You see it? Why? Because here we do not have such kind of categorical. You know what I mean? What if we have a categorical, for example, gender? Luckily, we don't have gender. And for gender, we consider, for example, 2 groups rather than 1 group. Then you're gonna see here we do have an age group. Let's see, where is the age? Age is here, but it's considered as somewhat like continuous. I know it's not exactly continuous, but consider, let's say, from 20 to 60. It's a lot. What if we group the age to be 3 groups, from 0 to 20, 20 to 40, 40 to 60? Then in this case, you know what I mean? It's somewhat, it's not a proper, you claim it to be, 0 to 20 to be 1, 20 to 40 to be 2, 40 to 30, 60 to be 3. No, in some cases, you will have a serious numerical problem. A better way is what? A better way is to code it to be, for example, 3 coefficient. And then use 1, 0, 0 to indicate 20 to 40, 0 to 20, 0, 1, 0 to indicate 20 to 40, and 0, 0, 1 to indicate 40 to 60. In this case, you can avoid a lot of numerical problems. But if you do in this way, then you need to consider, interpreting this, let's say, suppose it's called beta 1, 2, 3. You need to consider this beta 1, 2, 3 together instead of using this method one by one by one. And how to confirm that they are really significant or not, you're going to confirm by this way, using the F-test. Clear? So this part is very, very applied, actually. Any questions about the statistical part? No? Okay. Then let's go to the mathematical part here. I'm going to introduce 2 types of decompositions. The first one is Cholesky decomposition. Yes?
Yeah. I just want to know why the equation number 21 is like in this form for t-test, like beta over sigma and roots. Why this tj is representing by this combination of beta and sigma, and why this equation like this form?
That's a good question. Let me ask you questions, and then you're gonna know why. First of all, what are the distributions of beta?
Normal distribution.
Okay. Suppose. How about this? How about we have a look at the same, whatever. Okay, normal distribution, right? For normal distribution, suppose we don't have sigma. How would we estimate it? We use t-distribution, right?
Yeah.
Okay. Now, if now it is the normal distribution, and then let me ask you, what does it follow? So the mean is beta, right? Okay, yeah. And it's unbiased. And what is the sigma? Sorry, what is the variance?
This
Get
one.
a point?
Yeah.
Get a point? Now let me ask you, for one beta j itself, what is its variance? This is a covariance because beta is a vector, right? I ask you, what is for beta j? What is its variance?
J diagonal element.
Yeah, j's diagonal element times sigma square, right? Sigma square is a number, okay? Is a number. Okay. Now, isn't it by the central limit theory? Actually, t-distribution the same. You just change the sigma to be sigma hat. No difference, right? Isn't it this number and the square root of sigma square, which is the sigma itself, right? And what is the sigma itself? It is sigma times the square root of j's diagonal, isn't it? What I mean is this. It's going to be the sigma square, square root of sigma square of, what is my notation there? I forgot. Cos or something. Cos maybe. Cos j.
Yeah.
Right? And then it's equal to what? Take a sigma out. Of course, you need to have a hat because it's a t-distribution. And then have this one. This is a constant, okay? Not estimated number. This is an estimated number by the equation here. By the equation here, okay?
Yeah.
And that's how you get this number. Clear? Yeah, that's it. Any other questions? Okay. Now we're gonna go to the decomposition part. Here we're gonna introduce 2 decompositions. One is the Cholesky decomposition, and the second one is the QR decomposition. So as I mentioned many times, there are 3 very, very important, most important decompositions. The Cholesky, QR, and also SVD, singular value decomposition. And SVD will be introduced in the part of PCA because PCA is demo as far as I know, is the most important applications of SUV. SVD, SVD. And in many cases, SVD is defined by PCA actually. Okay. And by the way, another very important type of the decomposition is LU decomposition. But LU decomposition is rather simple because it's nothing but the Gaussian elimination. So that, you know, in many fundamental linear algebra textbooks, I guess you have already learned it. So here, I don't think I will really mention it. So what is the point for us to considering this? Why do we need to do it? The main reason because in the OLS estimator here, we have an inverse matrix. See it? And again, once we see inverse matrix, we'd better be careful because a brute calculation may be very, very painful. And by the way, Arab, in your midterm exam solution, did you see my comments that I sent you yesterday? Which I forgot. You directly use the inverse matrix, okay? Although it's not wrong, but my point is to let you run this IRLT algorithm. You know what I mean? So have a look at my my comments and try to recode it. Okay.
Okay.
So and you use MATLAB, right? MATLAB, it has its own the quadratic programming solver. Okay. I think they use the ADMM, or I'm not pretty sure, whatever, or maybe any interior point method for this type of for this type of the quadratic problem. It's very standard and it's extremely simple. You know, to be honest, you can use whatever method you want. Okay, so in order to make this one easier, we need to decompose this XTX matrix. And here are two standard methods. One is by Cholesky, the other is by QR. Okay, let's first have a look at the Cholesky decomposition. By the way, I had a look at the pronunciation of this. Different professors have very different pronunciation. I remember when I was a student, there was a Russian professor. His pronunciation is Cholesky rather than Cholesky. Probably he's correct because this name looks like a Russian name. So maybe it's called Cholesky decomposition. Any one of you know Russian, by the way?
No.
No? Okay. So but for me, because you know, in terms of English pronunciation, I still call it a Cholesky decomposition. Please, you know, excuse me, or later if you become a professor or teacher, you are welcome to read it as a Cholesky decomposition. Anyway, so the point is this: if I have a matrix A, which is a positive definite matrix, S plus plus means positive definite. If there's only one plus means a positive semi-definite, okay, symmetric. And then there exists a unique lower triangular matrix L with positive diagonal entries such that A equal to L LT. What I mean this, you can simply have a look at this, which is easier. So this A is positive definite. And it tells you that I must have unique such a lower triangular matrix L. So this is unique. This is lower triangular. So of course, LT is upper triangular. Okay. And this equal to this. So this is a Cholesky decomposition. Okay. Any questions? First of all, no? You are not curious about, for example, why this is correct. How can you prove it? This would always be the first question you want to answer. You want to ask when you learn something new. You know what I mean? Don't just follow it. Instead, challenge it. Because challenging is a great way to discover and to learn. The best way to learn is to challenge. Anyway, regarding why it is correct and the proof, actually itself is a proof. And we're going to see in several minutes. Okay, so first of all, assume this is correct. Now let's see how to calculate it. Because what I want to find is this L, right? In other words, I want to find these Xij's, sorry, Lij's, where I is less than or equal to J. Okay, so because I have this A is symmetric, so I must have Aij. I must have Aij equals to Aji. Without a loss of generality, let's assume I is greater than or equal to J. Okay, so excuse me. So simply by the definition of matrix multiplication, you must have this. Okay, so this is nothing but the matrix operations, okay, which I focused on Aij. and this equals to this. And you know, here the part is still n, just by the definition. But because L is an upper diagonal matrix, it's meaningless for me to calculate anything is greater than j. Why? Because the minimum of ij equal to j, right? So I only need to count till j. So I have 26 first. Then by 26, suppose I and j are equal. What do you have? Simply, you have this, right? Okay. What you're gonna do is that to decompose it to be two parts. Consider this j is I, okay? Which is k from 1 to j minus 1 plus j equal to I itself. So that you have this. If k equal to I minus 1, so this becomes square. And if it's itself, I take it out. Why I take it out? The reason because I want to have this formula. So that I can directly calculate LII. LII equals to this. ARI minus this in the square root. Clear? The question is what? The question is, I have a LIK here. In other words, in order to calculate LII, I need to know LIK. You know what I mean? In other words, is this. Suppose I want to calculate, for example, L22. I have to know L21 first. In order to calculate LNN, I have to calculate all things before. See the point? Because of what? Because of 27. Very simple. Okay. Okay. Now let's have a look at the second case that, again, from this equation, from this 26 equation, what if I is not equal to j? Again, without the loss of generality, assume I is greater than j. They're the same, you know. Okay, so in this case, first of all, still I decompose this one to be this part. Okay, from 26 I get this one, and then this one, the reason that I can take the ILIJ out and write it in this way. Clear? And then I can write it in this way. Okay, so in this case, I have, guys, you know what? I made a mistake just now. I made a mistake just now. I just realized there's a, sorry, what I said just now was wrong. What I said this way, right, was wrong. Here, the case is that you should fix I and count from k equal to, give me 1 second. You should fix I, count from I to, this is correct. Let me see. But how to solve the logic issue here? Because to get LIJ, you need to have LJJ as well. Let's say, for example, suppose you have, oh, yes, no problem, yes. So first of all, to get this one, I need a line. To get this one, I need LIKs. However, don't forget that L11, I always know it. L11 is super simple. It is this one square root, right? Okay, and now I can get L11 first. After getting L11, what can I do? I have LIK equal to this. And to get this, you do need to have this, LIK and LJK. And you need to LJJ. However, don't forget that here I have I is greater than or equal to j. In other words, it's somewhat like this way. Your I is the rows, your j is the columns. So that in order to get this number, you need to get numbers before it. So if that is the case, it gives us a very beautiful order to calculate. We can calculate it in this way. I first get L11, then I get L21, and then I get L22. And then I get L31, and then L32, L33, blah, blah, blah. And then I get LN1, LN2, until LNN. You know what I mean? If you have a look at the formulation here, you're going to see in this order, we can easily get everything. For example, L11 is very simple. Let's have a look at L21. What's going to happen? L21 equal to, okay, so L11 I've already known, right? And then 21, of course I know it, minus here, k equal to 1, because j equal, no, here's, let me see, here's, let me see, 2, 1, right? So here, this part is done. So you immediately get what? You immediately get L21. To get L22, you have this. Because what? Because you already have L21. See it? So the second row is done. And you can use the same way. You can see third row, fourth row, everything's done. So that by this formula, we can actually calculate by rows. And hence, here we go. And then here's the order. Row 1, row 2, row 3, until row n. In this case, we're going to easily calculate all of them. And this algorithm actually, just shows this idea very clear. Okay, and this is actually a great proof that the Cholesky decomposition does exist. However, to be honest, this proof is not strict. Why? Because I didn't use the part that A is positive semi-definite. For strict proof, you need to use induction. Okay, any questions? Induction in terms of n. Any questions? No? Okay, so now I need to mention 3 points. The first point is what I just mentioned, that itself is a very rough proof. In terms of calculation, again, it's not strict. Rough proof of the existence of Cholesky decomposition. And the second thing is that be careful, suppose A is not positive semi-definite. What I said is positive semi-definite, okay? Then it doesn't have a Cholesky decomposition. Anybody knows why this is correct? Actually, the proof is right here. Just 2 steps, you can finish it. Let me open the Word. Give me 1 second. Why it's here? Move it a little bit here. Oops. This is a problem of doubles. Okay. Now suppose if A is not in S plus N. And suppose we have Cholesky decomposition. Then what's going to happen is that for any x not equal to 0, we have what? We have xt a x equal to what? Xt l lt x greater than or equal to 0, right? This part I don't mention, right? This is too simple. This is what this is xltt times itself. You know what I mean? This equal to this something times something t itself. Okay, where something is what? Something is x ltx. Right? Then this is a contradiction of what? Of x a is not a positive semi-definite. And hence, if it is not a positive semi-definite, you do not have a Cholesky decomposition. Clear? Contradiction. Contradiction. Okay. However, be careful that if A is really positive semi-definite, what I mean is, then what you will where it is? Where's page 8? Oh, okay. Great. Page 8 has hide it here. Great. Be careful that if A is positive semi-definite, then your decomposition may not be unique. Why? Because you may have some problems here. If a matrix A is positive definite, then all diagonal elements must be strictly positive. However, if it is positive semi-definite, then the Aij could be 0. And once ARI could be 0. Once ARI is 0, what does it mean? That means all of these must be 0. And you're going to have a problem here because you're going to have 1 divided by 0. And usually, if you have this kind of case, that means multiple solutions. Okay. Of course, for a strict calculation or for strict proof, again, you need to take advantage that A is positive semi-definite, and then you need to do a lot of algebraic, work here. And I'm gonna, ignore this part here, but you can easily find some calculations. For example, defining ARI equal to 0 and trying the Cholesky decomposition, you're gonna find something very, very interesting that it does not work. Or if you directly simply apply this equation itself, and it's gonna cause a problem. And that's the reason why here in theorem 9.1, we require that A is positive definite instead of positive semi-definite. So we have a unique Cholesky decomposition. Okay, any questions? No? Okay. The second one is QR factorization. For the QR factorization, first of all, let's have a look at the full QR factorization. The theorem is this. So suppose a matrix A is in Mn, then there exists an orthogonal matrix Q, which is Rmn, and upper triangular matrix R, which is m by n, such that wait, I missed an R here. Let me change it. So let me see where it is. QR factorization, then it must be R and F. Seriously? Oh, okay, it's here. R is here. Let me code the compile it again, and then the R will be coming. Go back. What happened? Run it. Okay, so by upper triangle matrix this, so that A equals to QR. What does it really mean? Let's have a look at an example. So I'll open the MATLAB here. So suppose, make it smaller. Suppose I just make any random matrix, X equal to, let's say, 5 by 3. Okay, so this is X. And then let me use QR. QR equal to the QR of X. See it? First of all, see the dimensions of Q. It's a 5 by 5. See it? And R is what? 5 by 3. So clear? Q is this and R this. And the second thing is Q is orthogonal. Why Q is orthogonal? Simple. Q times Q prime, or Q prime times Q. This is the identity matrix. That's why Q is orthogonal. R is, of course, upper triangular. This is very easy to see. R is upper triangular, okay? So this is QR factorization. Different from the Cholesky decomposition is that QR factorization exists for any matrix. Okay, so, excuse me. So we call this one as a full QR factorization because the size of Q and R's are large. Actually, we can have a much smaller, more economic QR. Before introducing this, let's review something about the linear algebras. First of all, is the definition of span. So suppose I have A1 to AN as the basis of the space. The span of them means using the linear combination of this n basis, whichever node you can reach in this n space, Rn space. Okay, so this is the span. And then is the definition of the range and the null. Range is actually similar to span, that with these A's, which can you get in the whole Rn space? So this is the range. So the difference is that range is the language about a matrix, and a span is usually a language about the collections of vectors. So that's the only difference. And null space is for a matrix as the x such that Ax equal to 0. So it is the null space of A. And then we also have the orthogonal complement. And orthogonal complement is defined in this way. Suppose suppose X is in set S, and the orthogonal complement of the space S, subspace or space S is defined in this. all the y's such that ytx equal to 0. Okay, and this is a very important conclusion, that the complement, orthogonal complement of the range of a matrix must equal to the null space of the transpose of the matrix. A very beautiful geometric interpretation of this conclusion can be shown here. Any questions? No? Okay. By the way, this is a 3D. You know, this is a 3D picture, not 2D. Okay, so this is a space, and this is orthogonal to it. So first of all, very clear, this shaded area is range A. A means A1 and A2, right? By linear combinations of A1, A2, you can get to any point in this space. Okay, and then very clear, this Y is the range, sorry, as the orthogonal complement of the range. Why? Simply because, you know, for anything in this range, it's vertical, it's orthogonal, so that Y is in the range of A. Sorry, Y is in the orthogonal complement of the range of A. Now have a look at this. Suppose you have an AI here. Calculate what is AI inner product of Y. Very clear, AI inner product of Y is 0, right? By the way, this 0 should not be above 0. It's a number 0. It is indeed a 0. In this case, have a look at the null space definition. Get a point here? That's why your Y must be the null space of AT. And that's the reason why this equation 33 holds. Clear? Okay, so why do we need to see this? Because after this, we can explain the thing QR factorization. Let's start from the full QR factorization first. So as we mentioned here, we do have a QR factorization for A. Now for the thin QR factorization is, I denote Q equal to Q1 and Q2. I decompose it to be 2 parts. And I decompose R to be 2 parts as well. By the way, if you use the notes before, I have a typo here. Before I wrote this one to be M and that one to be N, which is wrong. Be careful, because we know that M is greater than or equal to N. So that this, you know, Q1 would be N here, N columns, and the Q2 will be M minus N plus 1 columns. Okay, so sorry, M minus N columns. So that's the reason why Q1, you know, and Q2 together becomes Q. And R1 means the first N rows of R, and R2 means the last M minus N rows of R. Oh, Jesus, I have a typo here as well. Let me see. No, no typo here. This is correct. This means the N plus 1 to N rows, and this means all columns of R. So that you will have R1, R2 gonna be R. In this case, what you're gonna have is that the span of the A's for any K less than or equal to N equal to the span of this, of the first, these columns. And hence, the range of A equal to the range of Q1. And because of this theorem, you are gonna have this part as well. The range of A orthogonal complement equal to the null space of Q2. Okay, so equal to the range of Q2, because the range of Q2 equal to the null space of Q1. And hence, you have what? You actually have A directly equals to Q1 times R1. And this is thinner than the full decomposition, the full QR decomposition. Why? Because my Q1 dimension is what? Q1 dimension is M times N. And my R1 dimension is, okay, let me write it down. Here, I need to write it down. I wish I have a whiteboard. Will make my life much easier. For a full QR factorization, let's say, first of all, let me write it in this way. A as A. A as in where I have the R here. R m by n times n. And I assume that m is greater than or equal to m. Okay, so for QR decomposition, I have what? I have Q as in Rm by m. Yes. Then R as in m by n. Yes, this is correct. Okay. However, in the thing QR factorization, we have what? We have Q as in m by n and R as in m by n. See it? Very clear, it's smaller because m is greater than or equal to n, okay? So m by n is what? Is something very thin. You know what I mean? It's gonna be something like this way. In the previous case, you have Q as like this, and your R as like this. This is for the full QR decomposition, okay? And in the thin QR decomposition, you're gonna have this. You're gonna have, give me a second. No, sorry, my notation here is wrong actually. Let me see. For a full QR decomposition, you're gonna have this. This is your Q, and your R is this. And for a thin QR decomposition, you're gonna have this. You're gonna have Q as in R and M, M and M, but your R is even smaller. Your R is gonna be in this way. So clearly, this one is more economic. This is a thin QR decomposition. Okay. So and let's go back. It is described here, and let's go back to this MATLAB illustration to see what does it show. So let's find what is Q1. Q1 equal to what? The first n rows, columns of Q, right? So what is my m? Here my m equal to 3. Sorry, 5. I have my x is 5 by 3. I have 5 rows and 3 columns. So that means the first 3 columns of Q. Okay, so we can click. Huh? Wait, mistake. Q1 equal to, reverse. All rows and 1 by 3. This is correct. Yeah. So that's your Q1 equal to the first, where's your Q? The first 3 columns of your Q. And your R1 should equal to what? Equal to the first n rows of your R. So that means 1, 2, 3 rows and all columns. And then I claim as A equal to Q1 times R1. Let's see whether it's correct. So that you have Q1 times R1 minus X to see whether it's 0. See it? It's almost 0. This is e to the power of negative 15. See it? That tells you that, hey, you can simply use this small q and a small r instead of such a big Q and a big R. It's clearly more economic. You know what I mean? And the proof is very, very simple because you can simply observe actually already. Look at your R. Your R is upper triangular so that only this part is meaningful. The other part is 0. It's simply just 0. So anything times 0 is 0. And because of that, you're gonna have only this part is efficient, is effective. Why? Because these 2 parts gonna multiply by 0. So it doesn't matter what are you. So no matter what is the case, you always have Q1 times R1 equal to A, and of course it equals to Q times R. See the point here? So this is a very simple indication. Yes. Any questions? Hello?
No question.
Okay. Okay. So then the thing is this. Then the thing is we have. Said, is that you?
Read this.
Sorry, who's talking?
It's not from here. I don't know.
Come on. Don't use X words. Anyway. Okay, so I muted. Okay. So after introducing the QR full factorization and QR thin QR factorization, the question is how to calculate it, because this is just a theoretical result. We need a method to clearly calculate it. Yes, today I'm going to introduce the Gram-Schmidt process. Have you ever learned the Gram-Schmidt process before? Probably you have had in your middle school, but maybe at the time the teachers didn't tell you this is the Gram-Schmidt process. I remember the first time I learned it actually in junior middle school, not even high school. The problem is that nobody knows this is called Gram-Schmidt. And later in undergrad, we learned in the geometric class, we learned this method, and they said that this is Gram-Schmidt process. And I asked the professor, I said, hey, isn't it just let me see how to translate it to English, kind of like stepwise orthogonalization? And he said, yes, that's the point of Gram-Schmidt. And that usually when I was in middle school, I call it stepwise orthogonalization. And you're gonna see why this is correct. So first of all, let's have a look at the QR decomposition, the thin QR decomposition. By the definition here, I should have A1 to AN equal to this, right? This is the definition of thin QR decomposition, where Q is n columns and R is n by n, upper triangular. Okay. And then we continue, just use the definitions. I should have this, my AK equal to this. Okay, and corresponding, I just move some items, I would have this. Okay, by the definition, my Q must be an orthogonal matrix or orthonormal matrix. Okay, by the way, something I want to mention is here. In this lecture, I still call A as orthonormal, but be careful, this name is not that professional. A more professional name for matrix is called directly orthogonal matrix. Sometimes, okay, it's called orthogonal because orthonormal is a term for columns usually. The reason I still call this matrix to be orthonormal is to indicate that the norm of each of its column is 1. Okay, that's the reason why I define this Q matrix to be orthonormal matrix. And A is upper triangular, no problem. Here, since my QK must be orthonormal, you must have what? You must satisfy 2 conditions. Condition number 1 is that for any 2 columns, QK and QJ, their inner product must be 0. This means QKT times QJ must be 0. And the second thing is for any QK column, the norm must be 1. That is the definition of orthonormal, right? Okay, so in other words, I need to find an RK because everything is known, only RIK and RKK are unknown, right? Once I know the RIK and RKK, I immediately know how to calculate QK. And I can start from Q1 and then Q2, Q3, Q4. So the QR decomposition is actually a question to figure out what are the values of RIK and RKK, right? Okay, now let's see how to figure it out. You have many different ways to do it, but the Gram-Schmidt method is choosing this way. First of all, let's have a look how to choose RKK. Choosing RKK is very, very simple because I want to make all the QK to be 0. Sorry, all the QK norm to be 1. And I already have a vector here. This is a vector. So pretty simple. How can you calculate? How can you get this RKK? Easy. Make RKK to be the norm of this one, right? If you make RKK to be the norm of this one, then of course the norm of QK equal to 1. You know what I mean? What I mean is this. Suppose I have, let's say, Q equal to, let's say, A by R, whatever, where A is, let's say this, that's A by norm A. Okay, Q norm. And the question, what is norm of Q? So that the norm of Q equals to what? the normal of everything, right? The normal of this. Norm. And what is this? Isn't it equal to 1? Why? Because norm of A itself is a number. This is number, okay? Norm of A, the numerator, denominator is a number, so that it's equal to the norm of A over the norm of A equal to 1. Okay, that's the reason why as long as I take RKK to be the norm of this, then the QK norm must be 1. So we figured out what is RKK, super simple, which is here. However, to figure out RIK is not that easy. And in Gram-Schmidt method, we take RIK to be this part. And you may ask, how did you get it? How did you think of that? Interesting thing is, in history, people didn't directly get it by observing, this equation algebraically. They got it from a geometric interpretation. And I cannot guarantee, but probably all of you have already seen this geometric interpretation in your middle school. Okay, think about this. Let's just have a look at this figure. And then after the geometric interpretation, let's see the pure math part. Have a look at this one. First of all, I'm going to let Q1 equal to A1 over its norm. So very clear, Q1 at the norm must be 1. Okay? And I fixed Q1 already. Let me draw something here. This means it's fixed. Okay. Now I need to go to Q2. To get to Q2, first of all, I will have a look at my A2. So this is again a plane, okay? So I suppose A1 and A2 get this plane, okay? They are on the plane. This is a 3D. So I make a projection of A1 onto the Q1. You know what I mean? So I have a shadow here. So the projection of A1 over Q1 would be this. In other words, this vector, see it? The green, the blue vector here, which is the projection of A2 onto Q1. So this is the length of the projection, A1 onto Q1. What is the length? It is the inner product of A1 and Q1. And use this length, and because Q1 is what? Is a unit vector. So the length times the unit vector equals to the real length of the vector. You know what I mean? So it's just consider that I have a light here. Come on. Can I draw something more interesting? Let's see. Suppose I have a sun here. Okay, suppose I have a sun. And the sun's gonna be this direction. Okay. That's too ugly. That's gonna be this direction. So isn't it? You're gonna get what? You're gonna get, this is A2. You're gonna have A2, you're gonna have a shadow of A2 on this Q1, right? Because Q1 equal to, Q1 and A1 are the same direction, so you can consider it they're the same. But the question is how long this is. The length gonna be A2 inner product of Q1. And this is the shadow, right? Of A1 onto Q1. Okay, now very clear, if I use A2 minus this vector, which means this part, the dash part, this must be perpendicular to this Q1. Get the point? You know what I mean? Because of what? Because of this. In 2D, it's going to be in this way. You know what I mean? So what I mean is this. So this is going to be A2. Oh my God, so ugly. This is A2. This vector is A2. And this vector is your Q1, right? So A2 projector onto Q1 is what? Is this vector, right? So isn't it, if A2 minus this vector, it is this vector, right? Isn't it this and this, they're orthogonal? You know what I mean? So in this way, yes, I get a vector already. I cannot tolerate my drawing. Let me erase all of this. And then yes, as long as I go along this dash line direction, yes, I must have a vector which is orthogonal to this vector. So in other words, I can guarantee this one must be correct. This Q2 inner product of Q1 must be 0. However, you need to have Q2 be what? Be a unit vector, so that I make Q2 equal to this part divided by its norm. Oops. This guarantees that your Q2 must be a unit vector. Get the point? Any questions? Please understand this point very, very clear. This is extremely important. Please stop me if you do not understand here. I can repeat it. Any questions here? No? Okay, very good. Now we can go to Q3. So in this case, I have Q1 and Q2. Now I must have what? I must have a Q3.
Do you have, can you hear me?
Yes, yes.
So I have a question.
Yes.
Q2 is the projection of inner
No,
product
Q2 is not a projection. Be careful, Said. The projection is this one. This is the projection. This is the projection of A2 onto Q1. Okay?
So
this
Q2 is the distance between A2 and
No. This is a vector. I'm talking about vector. I'm not talking about the distance. I'm talking about a vector. This is a vector. See it?
Yep.
Okay. This vector means what? Means I project of A2 onto onto Q1. See it? Remember, I just drew a sun here. Just imagine you have a sun. You have a light here. You shoot the light this direction, and then you're gonna get a shadow, right? And the shadow will be this. The direction will be Q1. The length is gonna be inner product of Q1 and A2, because Q1 is a unit vector. So this directly shows you the length, right? So your Q2 originally is this part, is A2 minus its shadow. The conclusion is if you use A2 minus the shadow, you must get a vector. You must get a vector which is this direction, which is this.
Okay.
See it? And this is exactly what we want. Why? Because this, I can guarantee this one must be vertical, must be orthogonal to Q1. And the second thing I need to guarantee is that, but I cannot directly set this one to be Q2. Why? Because this is not a unit vector. I need to make this one to be a unit vector. How to do it? Use this one divided by its norm. So Q2 would really be unit. And meanwhile, Q2 is perpendicular to Q1. Get a point? So I have finished Q1 and Q2. Now let's see how to do Q3. Exactly the same. First of all, I have A3. Again, this is a 3D, okay? A3 is not on the plane. A3 is something, tall, outside. The A1, A2 is a plane. A3 is something vertical, in the Z direction, something like this. So what I'm gonna do is first, I'm gonna project A3 onto Q1. Q1 is this direction. So this is, let me draw text here. It's really important. This is something A3 project onto onto which one? Onto Q1. Okay?
Q1.
Yes, thank you. And okay, so in this case, let me add some text here as well. Let me draw a point here. This is A2 project onto Q1 as well, okay? So this one is the project of A3 onto Q1. Jesus, if I move, it's gonna move as well. Whatever, okay. And how about this one? This one is
A3 project on Q2.
Onto Q2, very good. A3, not A2, by the way, it's A3.
A3, yep.
Yes, A3 project onto Q2, okay. Because your Q2 is this way, so that it onto it's this direction. And very clear, I must have both this and this. They're perpendicular, because it's a 3D, you know what I mean? Here I can only draw it in the 2D. It looks not clear, but indeed these things are perpendicular. Now what I'm gonna do is that I'm gonna sum this one plus this one. So this as the summation of this vector and this vector. And the thing is that if I use A3 minus this vector, I'm gonna get what? I'm gonna get this vector. And this vector must be perpendicular to both Q2 and Q1. Get the point? Why? Exactly the same reason. Because this vector equals to Q3 minus this and minus this. And hence, it must be orthogonal to both of them. You know what I mean? So we can decompose it to be two parts. Decompose it to be this part and that part. And both of them are orthogonal. So this yellow vector must be orthogonal to both Q1 and Q2. And hence, I can set Q3, and hence I can set Q3 in this way. Q3 equal to A3 minus this vector divided by the norm of this. This guarantees that first Q3 is perpendicular to Q1 and Q2. And the second, Q3 must be a unit vector, meaning that the norm of Q3 must be 1. And you can do the same, repeat it for Q4, Q5, and Q until Qn. And all of them are guaranteed to be the same, because here's 3D. I cannot draw 4D or 5D, so I cannot continue doing it. Okay, so this is a very beautiful geometric interpretation of the Gram-Schmidt process. Have you seen this kind of operations in junior middle school or high school when teachers are teaching you this kind of 3D geometrics? Did they do this? I still remember the theorem called I don't know the English name. I don't know how to translate that Chinese name to English name. It is something like the cosine theorem for the 3D. And it's exactly following this proof. The proof is exactly in this way. But at that time, nobody taught us this is called the Gram-Schmidt process. I didn't know it until I was in undergrad in I don't know which year, like the third year or the second year or something. And we learned geometry, and then we know this is this. Okay, so however, you may be unconvinced. You may say, hey, you just showed it in 3D. What if it's a 4D, 10D? Can you show it? Of course, I cannot show it geometrically, but I can show it algebraically. I didn't show it here. It's an exercise for you to do it after the class. Please use this formulation that RKK equal to this and RIK equal to this. In other words, I'm asking you to substitute 37 and 38 to 35C, so that you should have the formulation of QK, right? And first of all, QK, the norm equal to 1. This is super simple. Why? Because of this, right? And verify the second point, which is using this one, you must have QK and QJ equal to 0. Start from Q1 and then Q2, Q3, Q4. You only need to verify 4 vectors at most. You're going to see, indeed, QK times QJ equal to 0. Algebraically, you can verify it. Get a point? However, I don't want you brutally memorize these two formulas because it's meaningless. It's very, very difficult to brutally memorize it. What I want you to memorize is this figure. And I want you to forget this. Instead,
yeah, that's true. I have one question about figure.
Yes.
Yes, so that you determine the Q1 is direction is same as the direction of A1, right?
Yes.
And Q2 is like A2 minus projection of A2 on Q1.
Yes.
How this one is granted that the Q2 is perpendicular to Q1?
Let me ask you, as this one, this green, let me draw it as.
I'm saying about Q2, not.
No. I know what it is. You said how can you guarantee Q2 is perpendicular to A2 to Q1?
No, yeah, but Q2 is perpendicular to Q1.
Seriously, Arab? Seriously? Okay, let me ask you this. Consider 2D. Forget about 3D. This is your A2, right?
Yeah.
Okay. Now you draw a line, okay? This direction, this line. You make a vertical, consider you have light, you have a projection.
Yeah.
Projection, okay? From the projection, you get this line. Let me use another color. From the projection, you have this one.
Yeah.
Let me ask you, is this one Let me use the third color. Is this perpendicular?
This one.
Not here,
Yes,
but
yes.
it's
Yeah,
gonna be perpendicular.
It must be. No, it must be, because that's the definition
Yes, yes, yes.
of
Yeah,
projection. You know what I mean?
I get the
Here,
point.
what I mean projection means orthogonal projection. Okay, don't I mean you might have in geometry there are some different bases of projection. What I mean here is orthogonal projection. See it? Because
Yeah.
this is directly my shadow. So of course this, because A minus B is from B to A. So this one must be perpendicular to
Okay.
to that.
Yeah.
And
Yeah,
similar, using the same way, this one must be perpendicular to this and this. Get a point? So this is the geometric interpretation for the 3D. But for 4D, I cannot draw it. So that if you have a higher dimension than 4D, than 3D, then you need to use algebraic way, which is substitute 37 and 38 into 35C and really verify it. You can, as I mentioned, just try Q from 1, 2, 3, 4. And I guarantee you're going to find something really beautiful and amazing. The question is, you don't have to brutally memorize it. What I want you to do is to forget these two formulas. Instead, to draw this figure by yourself and verify it by yourself. Try to rediscover it by yourself instead of to memorize it. You know what I mean? So in this case, you will not forget the standard Gram-Schmidt method. Okay? It is as an exercise after the class. Please do it. Please very clearly verify these two parts. Okay? And the second method, I don't have time today, but the next time I'm going to introduce is a modified Gram-Schmidt method, because this method theoretically is very beautiful, but in application, it may have some, it may have some numerical errors because it's conditional number in computing. Conditional number is something to measure the stability, numerical stability. The conditional number of this one is large, indicating a relatively low numerical stability. So in some cases, suppose you have a very, very large, let's say, number of vectors, number of features. Let's say your A is high dimensional. It's possible that using this method, you are going to have numerical calculation error, and hence using this method, the Q and R calculated as not equal to the A itself. And because of that, we're going to use a modified Gram-Schmidt method. Both of these two people, Gram and Schmidt, both of them lived in 19th century. At the time, there was no computer. So of course, they did not realize there could be some numerical problems. And people lived in 19th century. They just feel theoretically it's beautiful. That's it, enough. You know what I mean? They would not, it would not be possible for them to calculate, let's say, after 50 digits. No way. But nowadays we have computer, and people immediately realize that there's something wrong. And then we modify it using another way. And hence we have the modified Gram-Schmidt method, okay? And by the way, using this method, you simply have all the Qs. This Q, Q1 to Qm as your Q1 matrix here. And you have your RKK and RIK, which is your R matrix here. See it? And hence you do have a QR thin QR decomposition for your matrix A. Okay? So, and I think the MATLAB gives you, oh no, MATLAB didn't give you this way. MATLAB did give you a full QR, but as we have seen here, this is a thin QR version of this one, okay? And in the next class, I'm gonna show why if we directly use Cholesky decomposition, or especially if we use the QR decomposition, the calculation will be much easier than brutally calculate the inverse matrix of this one. Okay, so this is everything about today's class. Thank you very much. And Mahbooba, I will have a meeting of you at about, let's say, 4:30. Give me about 10 minutes. I want to drink some water, okay?
Okay.
Thank you very much.
Ewan,
yes.
Can you hear me?
Yes, yes, I can hear you.
I emailed you about the time of the meeting tomorrow, about 11.
Yes.
Is it okay about 11?
Oh, sorry, so I forgot to email you back. Yes, 11. Yes, I saw it. Yes, the time is okay for me.
Okay. Yeah,
yes.
See you. Thanks.
See you tomorrow. Okay, so let me see. That's everything about today's lecture. Thank you very much, guys. Goodbye.
Thank you. Bye.
Bye.